So good afternoon, everyone. Let's begin our class now. Good afternoon, everyone. Let's begin our class now. So last class we were looking at how these, how the BJT can be, denoted as small signal analysis, and we can do small signal analysis on BJT transistors. So the hybrid pi model that we looked at. Okay, if you remember, we have the base, we have this resistor which we denoted as R pi, right? And we have this dependent current source. Let me use the typical convention, given as Gm times small VBE, and we also had R naught. So this becomes the collector and this becomes the emitter terminal. Now notice that in a small signal model, the first thing that we do is basically to, we do not have, the small signal model does not have DC information or DC bias information. Okay. Okay. So basically it means that all voltage sources, all DC voltage sources, okay, are considered as AC ground, all right, and all DC current sources to be open. Okay, so this is the convention that we will follow. Okay, so a small signal model of when we draw the small signal model of any BJT transistor or any transistor for that matter, or any circuit, we typically take we do not consider the DC current flow or the DC voltages here. We are only looking at the small signal incremental voltage. Okay, and we say that this is the VBE, and the small VBE is basically the incremental signal or the AC signal. Okay, the actual signal will consist of V capital BE plus the small VBE. Okay, in the small signal model, we do not take this capital VBE into consideration. Okay, that is eliminated from our representation here. Okay, the small signal model is only for the incremental voltage changes that happen around a given bias point. Okay, so just to recap, yesterday we saw that R pi can be derived to be beta by Gm, right, and Gm can be written as IC by Vt, and R naught also we saw that it was magnitude of Va by IC, correct. So for a given DC bias condition, right, you end up with a certain small signal parameters, basically Gm, R pi and R naught, and with that you can construct the small signal model. Okay, now today we will also see two other models. Okay, this is the hybrid pi model. Okay, a small tweaking we can do to this model. Okay, if you say that this is VBE across this R pi, and in yesterday's discussion we knew that there is a small signal IB which is flowing, correct? If you recall what we saw in last class, we saw that capital IB can be written as IB can be written as I capital B plus small ib. Okay, so this is the DC component and this is the AC component. Okay, the AC component is basically flowing through this R pi resistance. Right, now you can write, you can have another small signal model which is pretty much similar. You can say that there is this IB flowing into this R pi, okay, and this dependent current source can be written as beta times IB. Okay, and this is the collector, this is the emitter. Okay, so this follows very easily because the dependent current source value we said was Gm times VBE. Okay, now VBE can be written as what? Gm times IB into R pi. Okay, this is the way we can define small VBE. All right. Now we know that from our discussion yesterday, this GM R pi can be written as beta. Okay, and therefore we can say that this is equal to beta times IB. So some textbooks will say that the beta that you get from the transistor's data sheet, okay, the DC bias beta, okay, is not necessarily equal to the the AC beta that we see here, but for all practical purposes, we can just take them to be equal. All right. So GM R pi here is given as beta, and you can sometimes when you are doing certain calculations, it might be a little easier for you to write it as beta times IB, or sometimes it might be a little easier for you to write it as GM times VB. Okay, depends on the type of circuit in which the BJT is located. Okay, and if you can use either of the models, whichever is convenient. Okay, so another note on R naught. Okay, now R naught is actually given approximately as what? The magnitude of the early voltage divided by the bias current, right? Now typically this value is quite high. Okay, and what you would do is, like in many cases, you are not, when it is compared with the other resistors in the circuit, it was typically neglected. So that we will see, but what we can understand, at least the point that I would like to make right now, is that R naught value is fairly high. Okay, all right. So there is, these two are called as the hybrid pi model. There is also what is called as the T model. But before we go into the T model, let us look at the small signal emitter current. Okay, so again IE can be written as I capital E plus I small e, correct. Now this is this is very similar to what we have seen in with our this thing as well, right? Collector current also we wrote it as I is equal to I capital C plus I small IC, right? The same way we can write it for the emitter current as well. Okay, now the emitter current, okay, so here again we can write this as we can find out what is called as the emitter resistance, or the emitter current, the emitter resistance that is basically in this particular circuit. Okay, so the way we can do it is basically like this. Just give me a moment. Right. So IE can be written, this IE can be written as what? IC divided by alpha. Okay. Now this can be written as what? GM times VBE divided by alpha. Correct. Now if you look at the transistor, right? Now this is your, let's say, small signal VBE, and this is the small signal IE that is flowing. Okay. So if you were to stand here and look at the impedance from the emitter side, okay, you get what I'm saying? You have this transistor, right? We looked at the impedance from this side and we said that that is equal to R pi, okay? And we looked at the collector current, and then we saw that collector current has this relationship with this one, okay? When we look from the emitter side for a BJT, right, there is a certain amount of current which is flowing out of the emitter with a certain small signal voltage between the base and the emitter. Okay, so if you were to calculate what is this VBE by IE, okay, a notion of resistance or the impedance that is seen from the emitter side of a transistor. So what will you get here? You will get alpha by GM. Okay, now this is what is denoted as RE. Okay, RE is another small RE is another small signal parameter, okay, which is defined as the emitter resistance, the small signal emitter resistance that you see from the emitter. Okay, now you should not confuse this with the large signal or the DC bias values. Okay, remember all these are small subscripted, small lettered values, basically, which means that these are the incremental voltages and currents that we are talking about. Okay, the actual VBE will be some V capital BE plus small VBE. The actual IE is going to be I capital E plus small IE. Okay, so if you cannot say that this divided by this is going to be RE. No. Okay, VBE and IE have a different relationship. Okay, V capital I capital E, the DC bias current is given by IS by alpha e to the power of capital VBE by VT, right? This is the DC equation. But around the DC point, the linearized model of the circuit, okay, for very small signal amplitudes, okay, that looks something like this. Okay, doesn't mean that if you take a multimeter and measure the resistance between the base and the emitter, you will get alpha by GM. No, you will not get it. Okay, that is different. Okay, this is basically for the small signals around the DC bias point. What is the resistance that they will see? Okay, so this is defined as RE. RE defined as VBE by IE, and it turns out to be alpha by GM. Okay, and many cases it can be almost equal to 1 over GM. Okay, if alpha is almost close to 1, for practical purposes, sometimes you can approximate it to be 1 by GM. All right. So it is this is something that you should have in mind. Okay, if you take the transistor, okay, and if you look at the small signal impedances, okay, if you look at the transistor from the base side, you will get R pi, which is given by beta by GM, right? If you look at this from the emitter side, you get alpha by GM, okay, which is also called as RE, right? And if you look at this thing from the collector side, we saw in previous guy, it is R naught, which is given by magnitude VA by IC. Okay, so this is how the small signal impedances behave from different terminals of the BJT. Okay, so you should have this very clearly in mind. Of course, all of this are with certain caveats. That is assuming that the other when you say you're looking from the base, it is assumed that the emitter is grounded. When you're looking from the emitter, it is assumed that the base is at a small signal ground, and so on. Okay, all right. So this is the way that we derive the small signal impedances. All right. So now what we will do is, we started off with a very simple amplifier, right? So let us try to do the small signal analysis for this particular amplifier. We said a simple amplifier is looking something like this: VCC, we have an RC, and we have the same transistor. Okay, and let's say we have some RB, and we have the signal source here, VS. Okay, VS can be written as some capital VBE plus some VAC. Okay, or let's just call it a small Vn. Okay, all right. Now, shall we draw the small signal equivalent circuit for this particular circuit? Okay, the small signal equivalent circuit. So how will this basically behave? So first of all, let's draw the equivalent circuit of the transistor. Okay, the equivalent circuit of the transistor is what we have been seeing. It is R pi. Okay, this is GM times VBE, and VBE is basically what is appearing here, right? And we said there is going to be R naught here. Now this is our collector node, this is our base node, this is our emitter node. Correct? So far so good. You are clear about what is what, right? Now what we will do is, we have to fit in the other things. Okay. Now what I mentioned in the beginning of the class is that all the voltage sources, DC voltage sources, are considered as AC grounds. Now why is it considered as AC grounds? Okay, can any of you try to explain? Okay, the point that I made was
AC component is 0.
exactly. Okay, so DC voltage sources are considered as AC ground. Why is it? As someone pointed out, VCC has only one component, which is the, let's say in this case 12 volt or something, that has only the DC component. Okay, so you can, write it, you can, for better understanding, you can basically say that, my VCC is having a DC voltage source, which is, let's say, 12 volt. Okay, now this will give you exactly 12 volt and no AC component on top of it. And if there is some AC current, because it's an ideal voltage source, the way we understand it, right, or the way we portray use it in our schematics, like it will sink any amount of AC current without giving any AC voltage. Okay, so voltage is 0 for any amount of current, and therefore the impedance, okay, if you look at, let's say, the ICC current, okay, ICC current can be written as capital ICC current plus some small ICC current. Okay, but no matter what you have, you only have a voltage of 12 volt. Okay, which means the small signal impedance, or small signal, is basically 0. No matter what the current is, the voltage given by this voltage source is fixed at DC 12 volt plus 0 AC. Okay, and therefore DC voltage sources can be considered as AC grounds. All right. So now at the collector node, what do we have? We have this RC, right? This RC is connected to the collector, and the other end of RC is connected to VCC. Okay. Now, as we pointed out, here, of course, this is grounded. Let me just make it clearer, right? The AC voltage is basically, the emitter is basically grounded. Okay. Now we can say that this RC is also grounded. Okay. Someone put something in. Yeah, the lecture is recorded. Yeah. Now this RC also, one end of RC is connected to the collector, and the other end is connected to AC ground. Okay. Because this is an AC small signal circuit that we are looking at, and let's say this is our V out node. Okay, so the collector node can be labeled as V out. All right. Now, what about the input side? At the input side, we have some RB, right? So let's draw RB. Okay, and then you have your AC voltage source. Here, what you have is only small Vn. Okay, the capital VBE is not considered here because this is a small signal AC circuit. Okay. All right. Now let us derive the gain of this circuit. So already we had seen that the gain of just this, without this RB is Gm times RC. Let's see how we can derive it from the small signal circuit. Okay. Now, how can we write V out? V out can be written as what? There is all these things are grounded. So for the sake of clarity, I can just connect all of them together. Okay. What is V out? V out is basically this current being drawn from the parallel combination of these two resistors, right? Both these currents are flowing together into this current source. Okay, so V out can be written as what? It is written as minus Gm times VBE into R naught parallel to RL. Why is it minus? Because the direction of current flow is opposite to that of the polarity. Okay, V out is defined as plus minus in this direction. So if this has to be positive, current has to flow into RC to the ground. But because of the direction of the dependent current source, okay, V out is minus Gm times VBE into R naught parallel to RL. Okay, sorry, RC here. Okay. All right. Now what is VBE? VBE can be written as what? Vn times R pi divided by Rb plus R pi. Okay. All right. So we can substitute V out can be written as minus Gm times R pi divided by R pi plus RB into Vn into R naught parallel to RC. Okay. So the gain, voltage gain, or rather the small signal voltage gain, which is V out by Vn, can be written as what? Minus Gm times R pi by R pi plus RB into R naught parallel to RC. Okay. Now typically, R naught, RC, if you have noticed the values of RC in the circuits that you have already analyzed or solved in the past, okay, what is the typical value of RC? It's in the order of a few kilo ohms, right? Typically single digit kilo ohms. You would have seen circuits with 2.7 kilo ohm, 3 kilo ohm, 1 kilo ohm, something like that, right? R naught typically is in the order of kind of close to 70 to 100 K. All right. Typically, if you can look at the data sheet, every transistor will be slightly different. If you look at the early voltage, it will be somewhere in the order of 70 volt, 100 volt, 80 volt, something like that. And if you typically assume a current of 1 milliamp, 2 milliamp or something, you end up with R naught, which is in the order of tens of kilo ohms or almost 100 kilo ohm or something. Okay. So a good approximation is to basically say that my voltage gain, okay, let me just call it AV, can be written as minus Gm times R pi by R pi plus RB into RC. Okay. In the previous class, when we did our derivation, we did not consider an RB, right? We didn't have that RB. We just said that without the RB, it is directly going into the circuit, right? So in that case, you will not have this factor of voltage division, right? And therefore, you will basically have the, if RB is not present, okay, AV is basically given by minus Gm times RB, which is basically the same result that we got in the earlier analysis, where we didn't go through this small signal analysis. Okay, is it clear? Is it making sense? Right? So the way to analyze, you can, in fact, during the course, you will be doing quite a bit of small signal analysis on different types of circuits. Okay, what you will basically see is that you will not have you will have to first start with the heart of the circuit, which is BJT, right? And replace the BJT with the small signal equivalent circuit, set all the DC voltage sources to AC grounds, and set all the DC current sources to open circuits, okay, and draw the rest of the circuit, okay, and you will be able to analyze the circuit easily, okay. Now, please don't make the mistake saying that other things like the amount of current, capital IC is equal to Gm times capital VBE. That is absolutely wrong, okay. All this is only for the incremental thing, okay. The reason I keep repeating this again and again is because I have seen students, even after repeating many times, when you ask them to solve a problem, they'll go and just say IC is equal to Gm times VBE, where everything is in capital. Okay, that is wrong. All right. Now this is one circuit. Okay. Now let us try to build a proper amplifier. Okay. Let's try to build a full amplifier. Okay. I did not draw the T model, right? Oh, I forgot to do that. Okay. Let me just take a pause here and let me draw the T model with T model with earlier we saw what is called as the hybrid pi model. There is also what is called as the T model, which is a small signal equivalent circuit model. Okay. Here the model is like this. Okay. You have the collector, and as we would expect, you have Gm times small VBE, okay, as the current which is coming here, okay, that's the collector current, okay. And now here we say this is your base terminal, right, and this makes use of this RE, okay, in the emitter terminal, okay. All right. So this model is what is called as the T model. In order to kind of satisfy ourselves whether this model is correct or not, let's just try to see what is IB. Okay, what is small IB? Small IB can be written as what? You have Gm times VB. Okay, so this is This is VBE, right? So the IB can be written as what? Small VBE by RE minus GM times VBE. In other words, you can write this as VBE by RE 1 minus GM times RE. Correct? Now we saw that RE can be written as what? Alpha by GM. So GM RE can be written as alpha. So VBE by RE into 1 minus alpha. So this alpha you can kind of substitute as VBE by RE into 1 minus beta by beta plus 1, right? This can be simplified to be VBE by RE into, you will have beta plus 1 here, okay, and you will have 1 here, correct? Beta plus 1 RE into VBE into beta plus 1, VBE divided by RE into beta plus 1. Now what is RE into beta plus 1?
R
Basically
pi.
this ends up being R pi, okay, VBE by R pi, which is what we had in the hybrid pi model also. This is basically just to make sure that we know what we are doing. Okay, all right. So this is another T model. Basically, you can either use the T model or the hybrid pi model in your small signal analysis. As we will be seeing in the course of the class, sometimes it is easier for us to use the hybrid pi model. Sometimes it makes it a little easier for us to use the T model. Okay. So whichever model you are comfortable with using, you can basically use that. Okay. All right. So let's move on, and what I want to do right now is basically let us try to you can what I want to do is let us try to build an amplifier. Okay. Okay, so the question that we are trying to address right now is that design an amplifier using BJT, okay, where I want the gain to be 10 volts per volt. Okay. Now, what we can some assumptions let me give you. Let's assume that the Vs is an ideal input source. Okay. Which basically means that Rs is equal to 0. Okay, and let's say VCC can be taken as, let's say, 9 volt. Okay, and basically we need to design a amplifier. So we know that how can we design an amplifier? This is an amplifier which will give us gain. This is what we have been seeing. Okay, let's say we have a Vs here. This is RC, VCC. Okay, we have already seen that the gain equation is what? Minus Gm times RC. Correct. Actual equation will be RC parallel to R0. Okay. For all practical purposes, we can just say it is minus Gm times RC. Okay. Let me say it's a gain of minus 10 volts. All right. Now, can we design this particular circuit? Okay. Now, how can you pick the values of Gm and RC? Basically, you can say that there are infinite combinations of Gm and RC, correct? Which will give you the same voltage gain. So 10 is equal to GMRC. It's the product of two variables, right? You can have different variables for each of them. I mean, different values for each of them, and you will still get a product of 10. You can either take, one example can be, GM of 2 millisiemens and RC of 5 kilo ohm. You will get a gain of 10, right? Another option could be, GM of, let's say, 4 millisiemens and RC of, what do you need for this one? 2.5, right? 2.5 kilo ohm. Right. Let's take these two examples. All right. And maybe, okay, let's just take these two examples. All right. Let's take the first example. Let's say GM is equal to 2 millisiemens. All right. How can we get this GM of 2 millisiemens? How can we have our BJT to have a transconductance of 2 millisiemens?
IC is equal to 2 millisiemens into VT.
Correct. So GM is IC by VT. Okay. If VT is taken as 25 millivolts, right? What is the value of IC that is required? Can you tell me?
50 micro.
Correct. 50 microamps. Okay. Now let us take the, okay, let me take the other case of 10 millisiemens. Okay, in the case that you need 10 millisiemens, you need only 1 kilo ohm, right? Okay, all right. In the second case, you need a GM of, let's say, 10 millisiemens. Okay, if GM is 10 millisiemens, what is the current that you write?
250 micro.
Correct. You need a current of 250 microamps. Okay, all right. Okay. So now, how can we make, let's say, 50 microamp of current flowing through our transistor? Or how can we make 250 microamp of current flow through our transistor? How can we do that?
Sir, we can put a current source.
Okay. Where will you put the current source? This is my transistor. Let's say now you are in the lab. You have the transistor in your hand. Okay. I am giving you beta of, let's say, 200. Where do you want to put the current source? And I am now having RC. Okay. Now I want, my task right now is to make sure that this BJT is having a transconductance of 10 millisiemens or 2 millisiemens. So either 50 microamp of current or 250 microamp of current, I have to make it flow. Where do you want to put the current source?
Sir, at emitter.
Yes, you can put the current source at the emitter. Okay, VCC. All right. This is let's say 50 microamps in the first case, or it is going to be 250 microamps in the second case. Okay. Then so we have this AC voltage source. Let's say this is only a AC voltage source. Okay, let's think of it as some weak sensor or something. Okay. Is there something else that needs to be done? You can think about it. Okay. One option is, let me give one option in red. Basically, you can say instead of ground, I am going to connect it to minus VEE. Okay. And I will connect the input directly, right? And I will put some base resistance here. All right. Okay. And so then what happens is basically, okay, this is not ground. Yes. Minus VE. Let's say this is taken as plus 4.5 volts, or and you can take minus 4.5 volts, something like this you can do. Okay. And so this RB will take care of the DC current. Okay. You will definitely have some. Okay, this is a direct voltage source, so it will directly draw the current. Okay. And this is one way to do it. Okay. Of course, the question then becomes, how do you design this current source? Okay. How to design the current source? That we can basically, I mean, that we will see a little later in the course. Okay. This is one way to do it. Okay. But let's try to use a circuit or design a circuit which does not use a current source. Okay. Let's say without using current source.
Sir, what was the new need of RB in that last diagram? Exactly.
Okay, so one second. Somebody asked the question, why is the current source connected at the emitter? Because that was one of the solutions given by one of the students. Okay, how to make 50 microamp current flow through this thing. Okay, so that was the reason. So somebody had asked in the chat. That is the solution proposed. So I'm just working with that solution. Okay, the reason that you need RB is basically that, see, this IB that is flowing, right? IB will consist of I capital B plus the small ib. Okay, the small ib is given by the V in source. Okay, this capital IB also has to come from somewhere. Okay, many times it's not at all a good idea to take it from the sometimes, I mean, usually what happens is you will basically have a, so for the sake of for the sake of simplicity, I didn't put this RS. If you put this RS, okay, RS is fairly high. You don't want the base current to flow through RS. So therefore, you put another RB and connect it to ground. That's a way to bias the DC thing. Of course, this RS and RB will form some voltage division and all those things. Okay. So if you make it more complicated, you make, like, you have to bring all these other things into picture. Okay. So we will look at those things. Okay. But typically, one thing is, we can just say that I'm directly connecting to Vn, but that means the DC current is also flowing through the this AC source, okay, which is not a good thing. Okay. So typically, correct? So thanks for pointing out that. So basically, it means that you put a capacitor here, okay, and basically you have the DC current flowing through RB and only the AC current coming from the source. Okay, this is what you typically do for most of the sources. Okay, if you, let's say, take a microphone, or for example, if you take a microphone and you put some DC current through it, depending on the type of microphone, you can even damage it. Okay, condenser microphones of course can handle it, but some of the other things cannot handle it. Okay, or if, for that matter, if there is other sensors or something, this is not at all a good thing to push your bias current through the sensor which you are trying to amplify, or the signal source that you are trying to amplify. Okay, so the right way to do it is basically put a DC blocking capacitor. Okay, let's call it CV. Block the DC and have the DC IB coming from, let's say, this is where I capital B flows. This is where small IB flows. Okay. Somebody had a question. Okay, why did we put the capacitor? Okay, so the thing is, this small IB consists of a DC current and a AC current. Correct? You don't want to have the DC current flowing through your AC source. Okay, okay. No DC current should, or let's say DC bias current, okay, this is one reason. Plus one more reason is, you will be forcing a DC bias voltage across the AC source. This is bad. Alright. So if you didn't have this capacitor, basically what will you have? You'll have this B in AC source with this RB, through which, let's say a current IB is flowing, or IB dash is flowing, right? So this node voltage will not be at 0, it will be at slightly above 0 volt, okay, because of the voltage drop here, VRB here, okay, and that voltage drop is forced on your signal source also, okay. So that is always that's not a good thing. So suppose this is trying to establish a DC of 0, and you are trying to kind of short it with a DC voltage or something, depending on which of the elements is there, that will blow up. That's all. Okay. So always you have to make sure that the AC voltage source does not have, any DC bias current flowing through it or any DC voltage forced across it. Alright. So a typical, the more realistic scenario is like this. You have a certain source, it will have a certain source impedance. You put a capacitor to block the DC and then you bias it with whatever voltage you want. In this case, we are biasing it with 0. I hope you guys are able to hear me. Yeah. So you are basically biasing it in this particular example. You are biasing it with 0 volt here, and this is some RB going to this transistor. You are having a current source going to minus VEE, okay, and you have plus VCC, and you have RC. This is where you are taking your V out. Okay. So somebody said you can put a current source and bias this transistor. If you use a current source, this is the way that you bias your transistor. Okay. This is one way to do it. Okay. Another way to do it is basically if you are using a current source, let's say this is your input source. Let me call it as Vs here. Okay. This source has a Rs here. So you have to put a DC block capacitance. Okay. And then you can, if you suppose you don't want to have bipolar supplies, okay, that is you only have a VCC and no VEE, okay, this node is grounded. What you basically need to do is basically to give a bias voltage here, okay, through this RB, okay. This is one way by which you can do. Now we know that this kind of biasing is not a good idea. So what is the other way by which you can bias it? Sorry, I didn't put the current source here. Okay, you can do like this. Okay, you have to put a bias voltage such that you have capital VBE here, and this current source can basically take any amount of voltage across it. All right, so you kind of bias it like this. Okay. Now the third way,
DC current of 50 by beta plus 1, right? Forced in the
which one?
Base current. Base current 50 by beta plus 1 will be forced, right?
Yes. So the current that is flowing here will be 50 micro by beta plus 1 plus small IB. Okay.
But we need to have a collector current of 50 microampere. Then why like we have used emitter voltage source, the current source across in the emitter.
Okay, so you can multiply this by divide by alpha, and then you can add it. So that is a small change. Okay, once you are actually doing these things in practice in a lab, you will not see much difference between IC and IE. Okay. So what you are saying, basically what you are doing is you are forcing a certain amount of current through the emitter. Okay, obviously that most of the current is come through your collector, right? Or basically what are you saying? You want to put a current source here in the collector? Something like this?
Yes, sir. Can we do that?
Yeah, I mean you can do that, but we will see that this will also have certain other things like you can put an ideal current source, but the way in which you implement your current source will be little different. When we come to current source implementation, you will see that this will need a certain Vmin across it. Okay, so that is going to eat your headroom of your amplifier. Okay, so you can.
Yes.
There's nothing wrong. You can do that. Okay. All right. Now, suppose let me maybe conclude with this, and I'll continue in the next class. Okay. Design the amplifier without an ideal current source. Okay. So I will come to current sources, current mirrors, and all at a little later time. That time you will see that every current source, a real current source, okay, will have some shunt impedance, and also it will need some minimum voltage across it. Okay, nothing is ideal in the world, so that will eat into your headroom if you put it here. Okay? But you can. There's nothing wrong. Nothing which prevents you from doing it. Nothing wrong. Okay. That's another way of doing it. That's another solution. Okay. Now, can you design the amplifier without the ideal current source? Basically, you need an IC of 50 microamp in one case, and another case you need 250 microamp. Can you tell me any other way that we have already
Sir,
seen
we
something?
can fix that. We can fix VS, sir, the DC part of VS such that VS minus the DC part minus 0.7 divided by RE should be equals to 50 microamperes.
No. Come again.
Sir, supposing like let's say that we take VS, the DC part of our voltage source as 4.7.
Okay.
And then
You want to put
0.7 we dropped across.
4.7 volts here. Okay.
Yes,
Okay.
sir. And then 0.7 we dropped across the transistor. And then 4,
Okay.
and then we take RE such that our IE will be equals to 50 microamperes or 50 by beta plus 1.
You basically want the 4 volt here, basically.
Yes, sir.
Okay. Now, how can you do this slightly better? You're kind of getting it. You're almost there.
Voltage divider.
Exactly. Okay. This is something that you have done so many times earlier also. Okay. So basically, what can we do? We can say that I have a voltage divider. Okay. And this is my RC. Let's say this is my R1. This is my R2. We are working with unipolar supplies. That is, we have only one supply VCC, the other side is grounded. Okay. Now we put a capacitor here, DC blocking capacitor, and we have a VS here. Okay. Now there is one more problem here. Okay. If you look at the small signal equivalent circuit, okay, what I'll do is the time is up. Okay. So by this design, you can design it such that you have an IC of the desired value. Automatically, the GM will be fixed based on the IC value. Okay. Now, this I will continue in the next class. Okay, because it's already 1:40.
Yes.
Okay. All right. Okay. Any doubts, questions? Okay. All right. So, thanks everyone. Have a nice day.